Okay, lesson 7, we're now looking at double angle identities. So to develop the double angle identities, we could just use the sum identities where the two angles are the same. So if I have sine of A plus A, well, that's really the same as having the sine of 2A. So that means that I could do both of this for A and for A. And then see what happens is these are now really the same expression. So this simplifies to be 2 sine A cos A. So same thing would happen with cos A. If I wanted to look at the double angle there, make all of these A's. This would now be the cosine of 2A. And now this is just cos squared A minus sine squared A. So these are quite obvious as to where they come from, unlike the sum and difference identities. Okay, we're going to skip the investigation there. So at the top of the 642 here, it kind of explains why on your formula sheet there are 3 for cosine. So the identity for cos 2A can be expressed in 2 other forms using the Pythagorean identity sine squared A plus cos squared A equals 1. For proof of the other 2 forms of the identity, we just looked at before. So what happens here is we know cos squared is 1 minus sine squared, and sine squared is 1 minus cos squared. So they just do a simple substitution to get from this form to the other 2, but they are all on your formula sheet. Okay, example 1. So we're using these just like we did our other identities, really. And we can just use them to replace things and prove some Pythagorean identities. So we need to prove that 2 tan x over 1 plus tan squared x is equal to sine of 2x. So if we're looking at the left-hand side, so again, the workbook doesn't give us a ton of room to write down these proofs. We see that we can replace a few things with the left-hand side. We can replace tan with 2 sine x over cos x. And then you'll see on your formula sheet that 1 plus tan squared x is equal to secant squared x. So we can go ahead and replace that. Sometimes you try a replacement like that and it doesn't work. That's fine too. You could also replace tan with sine squared over cos squared and then end up making a common denominator, and the same thing would end up happening. So we're going to keep simplifying this. So 2 sine x over cos x is on top. On the bottom is now 1 over cos squared x. So now if we multiply by the reciprocal, we have 2 sine x over cos x times cos squared x over 1. One of these cosines cancels out, so this leaves you with 2 sine x cos x. Well, this is exactly what the double angle formula for sine is on the formula sheet. So we are done here. We didn't actually have to touch the right-hand side, because we can just say this is sine 2x. Example 2, use the identity sine 2a equals 2 sine a cos a with a replaced by 3x to determine the double angle identity for sine of 6x. So if I replace a with 3x, I'm really going to get an expression for the sine of 6x. So now if I'm going to use the double angle formula to express this, I can just say this is 2 times the sine of 3x times the cos of 3x. Now this is only really helpful if we know what the sine or the cosine of 3x is, but we can do it just like that. Okay, so we're going to write double angle identities for these 2 angles now. Cos of 10a, well, how could I write that as a double angle? Well, 10 is twice 5, so I could write this as cos of 2 times 5a. And then I can just pick one of the double angle identities for cosine. Sometimes one is more useful than the other. Here they just want one written down, so it's not a big deal. Well, what if we wanted to write something like this as a double angle? Well, how could I write 1x as a double angle? Well, I could write it as 1/2 times 2x, or 2 times 1/2 x would make more sense with how the formula is set up. So now 1/2 x becomes my input into the tan double angle identity, so that is 2 tan 1/2 x over 1 minus tan squared 1/2 x. I don't know why you'd ever want to do that, but that's how it can be done. Example 3, express each of the following in terms of a single trigonometric function. So we have 2 times the sine of 4x times the cos of 4x. So this is really our sine double angle identity. So that meant our double angle was 4x. So if I'm writing this as 1, I could write it as the sine of 8x. The next one looks just like the cosine double angle with an angle of 1/2 a. So this must have been cos of 2 times 1/2 a, which simplifies to just be cos of 8, which is a lot simpler way of writing it. Next one, we have sine of 5 over 2x times the cos of 5 over 2x. So this doesn't quite look like anything yet. It looks closest to the sine one, but without that 2 in front. So we have to make the 2 go in front by putting a 1/2 times 2 here. So this allows us now to say this is the sine of 2 times 5 over 2x, which is the same as 1/2 sine of 5x.